Alright, so in the last video we finished up Unit 2, which is like secondary differential equations, but now we're going to go on and move on to Unit 3, which is Laplace transforms. And it's actually probably one of the most useful things in this class, especially for engineers. It's used to solve differential equations like we've been doing, but in a easier way. I know you're looking at this like nasty integral right here and you're like, there's no way that's easier, but just trust me. But what's interesting about the Laplace transform is normally you have a function with a variable and you plug in like a number and then it spits out another number. Like f of x squared, if you feed in 2, then you get 4. Well, with the Laplace transform, it's the same idea, but instead of feeding in a number, we're feeding in a function. In this case, like f of t. And as a result, we get a different function, which is going to be defined in a different variable s. Some people just write s like that, but I give it a little curly, just so it doesn't look like a 5 or something. But what this does is differential equations, they can be ugly, like e to the negative x sine of 3x all over radical 3x, and you have to derive that and stuff. It gets really complicated really quick. But what this nerd Laplace found out is any function, no matter how complicated, can be redefined in a algebraic equation, like a polynomial, like x squared plus 3x, and etc., which is a lot easier to deal with. So that is what this function does. We're going to get a differential equation with derivatives and all the nasty stuff. We're going to plug it into this function and we get a algebraic equation. And then in the next unit, we'll do what's called a inverse Laplace transform, where we get like some function of s and it'll spit out it's what it used to equal, or like a solution to the differential equation. But it'll make more sense as we go along. But that's the gist of what the Laplace transform is. And I thought about proving it. I looked up a proof online and I thought about like copying it just to have it here, but I figured like if I'm just copying an explanation from someone else, like you might as well just watch that person who actually knows it. So you can look it up. There's a great video from an MIT professor that explains the proof to this. But let's jump right into it. So what this is saying is the Laplace transform, which is this curly L thing. You get this function that you put into it, and this is going to equal the indefinite integral from 0 to infinity of e to the minus st times that function you plugged in times dt. And notice we have two variables, s and t. We're integrating with respect to dt. But one thing I want to point out is this indefinite integral, you can't just evaluate it. You can't just plug in infinity and get something. You need to plug in the limit as it approaches infinity. So let's do that. let's say some variable like c as it approaches infinity, and the integral from 0 to c. This is the same thing, of e to the minus st, f of t dt. So we're just going to explain this with a basic example. And what we're going to do is just find the Laplace transform when f of t is just 1. So, as we plug that in, we're going to do the limit version so we can actually evaluate it. So, the integral limit of 0 to c e to the st times f of t, which is just 1, so times 1, but that doesn't change anything, so we can just write our dt. And, well, we can actually find this integral where this equals the limit as c approaches infinity of negative 1 over s times e to the negative st evaluated at 0 and c. And well, this we can just follow me down here is the limit as c approaches infinity, as so we plug in c into t and 0 into t, so, and we have to take the limit of it, so 1 over s, and you can check that this is actually the integral. You can take the derivative and you'll be left with e to the minus st, like the chain rule, you multiply it out. But negative 1 over s, negative s times c, and remember c approaches 0, minus negative 1 over s, e negative s times 0. And, well, e to the s times 0 is e to the 0, which is just 1, times, well, negative and negative is plus just 1 over s, times 1 is just 1 over s, and, well, we have like two cases here. When this approaches infinity, we have a negative exponent that's getting bigger and bigger and bigger. And we take the limit of that, and it's pretty much just saying 1 over s to the e to the s times like infinity. As this approaches infinity, this just approaches 0. But that's one case. That is when s is greater than 0. Now, if s is less than 0, then we will have a positive exponent, so this would actually be in the numerator. And, well, as c approaches infinity, the function also approaches infinity, which means it doesn't converge, so there is no solution. So, under the condition that s is greater than 0, we have the Laplace transform of 1 equals 1 over s. Now, this is going to make more sense as we do more and more examples, and you'll see like how it can be applied. But we're going to go over like the integral way like a couple times, just so you know where it's generally coming from and how to do it. But eventually, you're just going to have a Laplace transform sheet, just a sheet that has a bunch of defined like Laplace transforms that are already like figured out, and you don't need to memorize them. If you wanted to, you could plug them into this integral and figure it out for yourself. But like for example, on my sheet, and you'll be able to use it on your exam, if f of t is t to the n e to the a t, well then that equals this indefinite integral of e to the minus st t n e to the at dt. And that's a disgusting integral. You don't want to do that every single time. So they just figured we'll just give you it on a sheet. And this turns out to just be an algebraic equation. Turns out to just be n factorial of n minus a plus 1. So you're going to learn how to just use this sheet and these like definitions to go back and forth. But for now, we're just going to practice the integrals just so you know where it's coming from. In the next video, we'll do when f of t equals e to the at.